Hello students, it's Dr. Church and our unit today in physical science is on energy. One of my favorite units. It's a fairly lengthy unit, and so we're just going to jump right in and talk about energy, and hopefully this is going to be a high energy presentation for you. First section in our chapter on energy is energy and its forms. The question is, what is energy? I mean, we use energy all the time. There are all sorts of energy transformation processes going on in our bodies right this very second. The computer screen or device or whatever that you're using right now is using energy. If you have air conditioning in your home, it's using energy. The sun is shining outside my window right this second, and there's a tremendous amount of energy that's coming down and warming the earth, right this very second, and consistently and constantly. The gas in your car is energy. If you stand up out of your chair or blink, it's energy. The next time that your heart beats, it's using some form of energy. So what is energy? It's everywhere. It's all around us. How does it work? And how is work and energy and power related? What are some basic kinds of energy, and what are some of the forms that energy takes? So energy, how does energy and work and power, how are they related? If the transfer of energy is work, and it is, work and energy are related. They're the same unit. They're transferable back and forth. We can turn energy into work. That's how a motor works. We can turn work into energy. That's how a generator works. Power is the rate at which energy is transferred. So if I transfer more energy in a shorter amount of time, then I've got to generate more power. Now, we've talked about forces and we've talked about work. We know that force is mass times acceleration. If I'm going to accelerate a body, a mass body, then I've got to exert a force in it. The larger the force, the quicker it can accelerate a particular mass. When a force moves an object, work is done. We learned that in our last unit. So a little recap there for you. We know that the force has to be in the direction of motion in order for work to be done. And energy is basically the ability to do work. If we're going to do work, we're going to have to use energy, transferring energy into some kind of a force over distance, which we define as work. I love this little photo here because I love structural engineering, and I admire these people that can walk on top of that thing. And then I look at these cables that are holding that structure in place, that crane. If you look below, they're building this skyscraper, and they're doing work to lift a steel beam or to get concrete or materials from the ground all the way to the top. Requires a tremendous amount of energy, and it requires work to be done. One of the more common ways that we see energy transfer is a roller coaster. We're in the middle of our home quarantine pandemic. Nobody's going to the theme parks right now. Disney's closed down. All the theme parks closed down. One of our favorite things to do is to ride roller coasters. When work is done on an object, some energy transfers to that object. If we're going to lift this roller coaster to the top of the ride, then we've got to do work on it. But then I can release that work, and that energy can come back out, and it takes on a new form. We can go from potential to kinetic energy, which we'll talk about in just a minute, and that can give us a lot of fun on a roller coaster. So that's a work energy problem. Power tells us how much energy is transferred in a unit of time. This is the formula, and we can do some pretty simple calculations. Power is equal to energy transferred divided by time. I love this example because these sprinters are very powerful athletes because they're exerting a tremendous amount of energy over a short amount of time, and the quicker they can make that dash, the more power they're going to exert. So these guys are super powerful athletes. We often think of power lifters or weightlifters as being powerful, and they are, because can lift a huge weight, basically short distances, but sprinters are very powerful athletes, or high jumpers as well. So let's look at some different types of types of energy. The first type is kinetic energy. There are two basic types: kinetic energy and potential energy. So you definitely need to know that: kinetic energy and potential energy. And let's look at kinetic energy first. Well, what is kinetic energy? Kinetic energy is the energy of motion. So objects in motion have kinetic energy. And you can think just for a second, well, what would cause an object in motion to have more energy? Well, if it was a bigger object, a more massive object, like a transfer truck, or I don't know, a wrecking ball, that would have a lot of energy in it. And then you can think, well, what else? Well, the faster that it's going, the more energy it would have. Now, this particular picture is a bullet, and bullets are very small. They don't have much mass, but they're going really, really fast. So they can transfer quite a significant amount of energy. The amount of kinetic energy an object has depends on its mass and velocity. That's what we just said. So if you hit your thumb with a hammer, that's not a very massive object, but it can move pretty fast. That hurts. This is actually Bruce Lee, one of my favorite kind of heroes of my youth. Bruce Lee had the famous 1-inch punch. He was able to generate enough force, enough velocity in just 1 inch to knock his opponents over. So there's a video about him doing some of that thing. So just Google Bruce Lee 1-inch punch if you wanna see that for yourself. It's actually pretty amazing. But he's transferring his potential energy into kinetic energy by moving his body, his arm, and his fist, really, really fast. Of course, this is physics, so there's a formula for it. What is kinetic energy? Well, the formula is 1/2 times mass times the velocity squared. Now, don't miss that term. The velocity is squared. So the kinetic energy goes up as a function of the mass. How big is that object? How massive is it? And then how fast is it moving? How fast is it moving? What is its velocity? And that term is exponential. That's an exponential term. It is squared. Well, that's the first type of energy. What's the second? Well, it's potential energy. Two basic types of energy, kinetic and potential. What's kinetic? It is the energy of motion. Well, there are different forms of potential energy. Potential energy is stored energy. Energy can be stored in an object because of where it is or how big it is. Now, the first form of potential energy we're going to talk about is what's called gravitational potential energy. If we take the weight of that object, which is its mass times gravity, and multiply that by the height, then that tells us how much potential energy that object has. So this is the example of the wrecking ball. If I lift that wrecking ball higher, the height goes up, then the potential energy goes up. If I put a bigger ball on the end of that kind of the cable pendulum there, then it would have more potential energy as it's lifted. And so you can imagine that as well, that the higher you go, the more potential energy an object can have. A book sitting on a desk has potential energy. That's not a very massive object, but if that energy falls off the desk, then that potential energy will be released in some way through motion. To lift the book up onto the desk takes potential energy. Again, back to the example of the roller coaster, potential energy due to an object's height, gravitational potential energy. The higher you go, the more energy potential it has. The heavier the object, the more potential energy it has. So if you've got a really heavy, full roller coaster at the top, you probably don't realize this, but it has more potential energy. So when you release it, the fuller that roller coaster is, the faster it's going to be going when it gets to the bottom. So you want to get on the rides that are full with heavy people, and they will be going faster at the bottom. Well, there's another type of potential energy. So gravitational potential energy, that's one. There's another type, which is elastic potential energy. This is the energy stored in springs, like a bow and arrow is actually a spring. When you pull the bow back, there's green No, no, no. Who is that? That's not Green Arrow. That's Marvel. Marvel. Y'all gonna have to help me out with that one. I don't remember that guy. So um, that's terrible. I've seen all those movies too, but I don't remember. You'll have to help me. So when you pull the bow back, it puts potential energy into the bow and the string, and of course when you release it, the arrow picks up the potential energy, and that's translated into motion of the arrow. So that's a bow and arrow is a type of a spring. And of course, the normal springs like helical springs that you would see on the suspension system of a car, or just normal springs that are pretty much everywhere. So the forms of energy, major forms of energy, there are other forms of potential energy: mechanical, thermal, chemical, electrical, electromagnetic, and nuclear. So these are different forms of energy. So we're going to look at those really quickly. So remember, you've got categories here: um, potential energy, kinetic energy, energy of motion. Potential energy is energy that's stored in an object, and that stored energy can be like gravitational energy or elastic energy, and then there are other major forms of energy. So we're going to look at those really quickly. Well, mechanical energy is energy associated with motion and position. All right, so that's the sum of potential and kinetic energy. It's not limited to just machines, even though we call it mechanical, but it's, in a system, the sum of the potential and kinetic energy would be the total mechanical energy of that system. Well, what about thermal energy? Well, again, there's the word therm, which brings up temperature and energy, total potential and kinetic energy of all the macroscopic particles. So again, we have studied this idea of temperature, and we know that temperature is the average kinetic energy of the particles, and if we put energy into the system, it gets hot, okay? And that is actually thermal energy. There's chemical energy, okay? Energy stored in chemical bonds. Broken bonds release energy, and all chemical compounds store energy. I actually had a fire in my backyard the other day. I'll have a little video I can post for you. But that's chemical energy stored in the wood being released. And if we burn oil like gasoline, that will burn quite a bit hotter. It's storing chemical energy. There's electrical energy. This is energy associated with electric charge. That's what's in your electrical system of your house, or the energy that comes out of a battery, or it's the energy that's powering your device right now. So that's electrical energy associated with electric charges, positive and negative charges at the atomic level. Electromagnetic energy, this is what causes your microwave to be able to heat up your lunch or your breakfast today. It is the energy of the sun. It's the energy from radio waves. If you're picking up, you guys turn your radio on in your car. Well, what allows the radio to play the music or the talk show that you're listening to? Well, there's got to be energy transferred from a tower somewhere, or your cell phone. It's not magic, guys. It's not magic. It's an energy transfer system. Visible light is energy that hits your eye and causes a reaction on the retina of your eye that is translated to electrical signals to your brain that allows you to see objects. But that is a form of energy. X-rays, if you've broken a bone or had an X-ray, that is a form of energy. But those are all forms of electromagnetic energy that is able to travel through space in the form of waves. And then finally, and we're almost done here, nuclear energy. We have a nuclear power plant in Raleigh, and it's the energy stored in the atomic nuclei of really all matter. And that's Einstein's famous E equals mc squared equation. E is energy, is equal to the mass times the speed of light squared. And that speed of light squared is a really big number. So even a very small amount of mass can release a tremendous amount of energy, and that's how nuclear energy works. All right, a lot of material. Look at the forms of energy. If Yeah, you're going to see this everywhere. If you just start looking, here's what I want you to do with this lesson: is just start looking for those forms of energy that you find around you, and start learning to identify them in terms of kinetic and potential, and the forms of potential energy, elastic potential, gravitational potential, and then mechanical energy, and etc. And I hope this lesson has been at least a little bit interesting. You kind of see energy around you everywhere. And thanks for paying attention and giving your best on this. Have a good one.